All right, so a couple of things I wanted to point out. I posted the practice problems yesterday. The goals and videos and more were posted before, and I'm still adding to the videos and more page. So since last Sunday, I had first 4 videos posted. This is a video from class that I thought was a little bit different than the other ones there, so I posted that. And there's going to be at least one more video appearing on this page that's going to talk about that idea of making an error when we do a hypothesis test, and we're going to go over a couple of those in a minute. And then I wrote up a few pages where I typed up my step-by-step process like we just went through with the last few examples. So for example, here I have the short version that we did the last couple of days, and we're going into the slightly longer version. So with a proportion like we just did, you have to have some data to use. And the data I mentioned here is you got to have the sample size, you got to have the count of favorable outcomes, and you got to know what your null hypothesis is. Once you have those, we jump over to the StatKey test for a single proportion here. And like we did a moment ago, we went to edit data, we put in our count, our X, our sample size, our N, and oops, I know I didn't put anything there. Oh, fine. For example, and then we go up here and we set whatever this is supposed to be. And then we run our samples. So this page just runs through the steps you got to go through to generate a hypothesis test where we just look at the p-value. And then down here I show an example of it. So I had this data, and I talked about this last class a little bit, that around 69% of adults in this February said they intend or did get a COVID vaccine. And the article also went on to say about 30% of people said they're probably not going to get the vaccine ever. It's a pretty big sample size, 10,121 people. That's a lot. And then I was wondering, like in my area, people tend to be more conservative, more Republican, and there's some evidence that specifically Republican males are less likely to get the vaccine than others. So it's more like 40 to 50% say they won't get it. So I was wondering in my area, is it higher than 30%? And so here I just run through an example where I say, okay, I got this sample where 18 out of 50 people in my area said they weren't going to get it. 18 out of 50 is 36%. Is 36% significantly higher than 30%? So I plugged that all into StatKey. And StatKey said, well, if you expected it to be 30% and you found 36% of 50 people, there's about a 22% chance that can happen. Like 22%, that's not that unusual. That's pretty close. So can I say based on that sample, can I say people in my area are more likely to not get a vaccine than 30%? The answer is no, I don't have enough evidence of that. In this case, I'm failing to reject the null hypothesis. So here's my by hand sketch that compares my p-value to my significance level, which we talked about today, and my decision and my conclusion. And then I have the source where I got the data from, that 30%. By the way, the 18 out of 50, I just made that up, sorry about that. But I just wanted to get a quick example of in here, kind of like we were talking about last class. And then let's go back. Oops, nope, not there. Come on, move out of my way, please. Hit the back button. There you go. And so I did a couple more pages like that where I just typed up the handwritten notes I do in class, but for different examples. So here I have a test for a mean, and we're going to do something similar to this one today in class today. Now this one right here is what we call a full hypothesis test. So instead of just getting a p-value and talking about the p-value, we compare the significance level. And in the next couple of examples, I'm going to be a little more clear about that in StatKey. So this is a little more than we've done until now, where I had a friend of mine, a realtor, saying, hey, but this is back in 2019, I think average home prices in Pendleton are around 20,000. So I went out and collected a sample over a couple of months of house prices in Pendleton, and I wanted to see, if I ran into StatKey, is it really much higher? And I found here that on the data I took, if I was expecting $200,000 for the price, and my sample data was $225,000 on average, is that much higher? And StatKey says there's about a 5% chance that can happen. And so I didn't mention this. What happens if your p-value is the same as your significance level? What do you do? you could kind of go either way on that. And typically, I would be in the more conservative camp and say, 5%, that happens sometimes. So I don't think the average house price is a lot higher than 20,000. Is it a little higher? Yeah, but not significantly higher. It's right on the edge of what's significant if 5% is the usual significance level. So, and that one's for a mean. And again, for the mean, you've got to have all of the data to run it. Now, unfortunately, copying this block of data in a StatKey is a pain because StatKey wants a single column. So a spreadsheet would have been a better way to have that data. So we'll take a look at that example. Or actually, I recollected data for 2021 to see what's going on, because it looks like housing prices have gone up since the pandemic in rural areas. So I collected some data on that. But that's not really the example I wanted to do. I just wanted to point out that these pages are here. They're typed up versions of my handwritten notes. I'm not the neatest writer, so sometimes I type stuff up. So this is kind of like a cheat sheet. How do you run a hypothesis test with StatKey? These 3 pages kind of run you through those examples. So check that out sometime. All right, so here's what I really wanted to look at. Let's see. And I discovered this study a few years ago. This particular article, and there's other ones, is called Mindset Matters, Exercise and the Placebo Effect. This was published in a Psychological Sciences magazine, and I don't have a subscription to it, so they're just showing me the abstract of it, not the whole study, and that's okay, because I found the data behind it, and we're going to take a look at it. So let's see what this says. So we have, in a study, testing whether the relationship between exercise and health is moderated by one's mindset. So 84 female room attendants working in 7 different hotels were measured on psychological health variables, how psychological health variables affected exercise. So those in the informed condition group were told that the work they do, cleaning hotel rooms, is good exercise, and it satisfies what the Surgeon General says about the recommended active lifestyle. So the work you do is exercise, is what they were told, right? And the Surgeon General says a significant amount of exercise is going to improve your health. The other group was not told this. And not only that, they told about, they went into specific examples of the work, what work they do is exercise. In the control group, they were not told this at all. They were just said, hey, we're doing a study. We wanted to just check some health factors about you. And they were measured in the beginning and they were measured after 4 weeks. And they measured things like blood pressure, body weight, body fat, hip to waist ratio, body mass index. They talk about down here. And the results seem to support the hypothesis that exercise affects health in part or in whole via the placebo effect. Meaning, if you're told doing this will help you feel better, then you're more likely to feel better, whether it actually helps or not. Okay, so I have a lot of friends who believe in energetic healing, auras and stuff like that, and that, you know, just putting someone's hands on you to heal you can heal you. Does it really work? They think it does. That's good. Right? If they do that instead of having an operation for cancer, that probably ain't good. But in other aspects of life, this, whether it really helps or not, just saying it helps actually can. All right, so let's look at the data. So the data, let's see, where did I find this again? Not there, here. Okay, so I'm gonna put a link to this page so you can go look at the data too. And I put the data in a couple of other places in StatKey just to kind of explore it for a sec. So where are we? Are in a randomization test for a difference in means. So this is test. And here's the link. And there was another study that showed just thinking about building muscle gained almost as much muscle. Yeah, I've heard about that too. And other things like watching somebody do like, I don't know, karate exercises, your brain is making those connections into how your body should move to do the same thing. So watching somebody do something can help you learn how to do it. There's all these different things about how our brain works, and there's some crazy stuff out there that's It's pretty remarkable. All right, so in StatKey, so again, I'm on the randomization test for difference of means. And then I had to switch to the data set called Mindset Matters here. So after you get that link I gave you, switch to Mindset Matters. And in the data, so I'm going to show the data table, they give a bunch of no's. So these are the people who are not informed that their work is exercise and that it matters. And we're looking at their change in weight over 4 weeks. So this person gained 0.4 pounds, this person lost 3 pounds, and so on. And then the no's are at the top, the yeses are at the bottom. I mentioned in StatKey that it takes whatever variable is first, calculates the mean, and then subtracts the mean of whatever was second. So in StatKey right here, and I'll write this down, they're taking the people who average weight loss of people who weren't informed minus the average weight loss of people who were informed. Okay. So that I had to look up and think about a little bit how that was being calculated. I took that data and put it into one of the descriptive statistics pages here, because I just wanted to see what does each individual data set look like. So the no's are down here. So these are the people who weren't told, and we're measuring how much weight they lost over 4 weeks. So we can see on average here, the median is almost 0. There's a bunch of people who lost weight. There's a bunch of people who gained weight. Now, these are the people who weren't told their job is exercise and this job will make them healthier. Then there's this group up here who were told your job is exercise. This exercise is going to make you healthier. This is a plot of their different weight changes. And it looks like more of these people lost weight than the people who weren't told it was exercise. Histogram version, you can see the difference in spreads here. These are more clumped around 0. These have much more variation from 0. So the question is, they both are 0 is in their intervals. Now these aren't confidence intervals. This is just the raw data. I did not run any confidence intervals here, right? So that's a whole nother thing we could look at. We don't have time today. So let's see. Oh, actually I did run a confidence interval. I didn't run them individually though. So here I put that data back into StatKey confidence interval for difference in means. And I said, okay, if we look at these differences, people who didn't know their work was exercise, take away people who did, what do we find here? So the difference in the averages, it's not the average difference, it's the difference of the averages, because they're different individuals, ends up being about 1.584. So what that means is the people who knew their job was exercise lost about 1.584 pounds more than the people who had no idea their job was exercise. In this confidence, so we're predicting, if you are told what you do is exercise, will you seem healthier? And here our measure of healthier is how much weight was lost. So if you were told your job is exercise and exercise is healthy, we expect that you will lose between, on average, a group of around 40 people will lose somewhere between ½ pound and almost 3 pounds is what we expect. Based on this confidence interval, do we expect there to be no difference in weight loss compared to people who knew it was exercise and people who didn't? That 0 ain't in this interval. So that's interesting. Let's go to the hypothesis test and see what happens. And let's just run it and then we'll write down everything. Generate, 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 generate. Now the sample data was already here. When we're looking at the difference of 2 means, the null hypothesis is also always, we just assume they're equal. That it doesn't matter whether you knew your job is exercise or not, your groups are gonna be about the same weight loss. And how many I got? 4,000, 5,000, 6,000, that's good enough. And then the question is, do we expect these people to lose more weight or so we have to decide what the alternative is, or do we expect there to be no difference? So before I pick the test, we got to think about this. All right, so mindset matters. This example is not in the book, so I can't refer to the book here. All I have is that study, and I can post a link to that study later. If you look up Mindset Matters, you'll find it in similar studies. And again, our population here, we have to decide what that is. Now, the study looked at a random sample of hotel workers, people who clean hotel rooms. So we could say the population is broader than that because we're kind of thinking about anybody that does a job where they have to move around and do stuff, or we have to restrict it. And so that can be a tough idea unless the researchers said, hey, this was our target population. So for population, I'm just going to put hotel workers. And parameter is average weight loss. And it's actually more than that because I'm comparing two groups. So average weight loss of people who think their job is exercise. And people who have no idea. So specifically, let's say we've got mu, let's call them E for exercise. So that would be the mean. And these ones where we look at two groups are always a bit harder. Mean weight loss of people who think their job is exercise. See there. And then we'll have mu no, N for no. That would be the mean weight loss of people who don't know. People who have no idea their job is exercise. They just didn't think about it. They weren't told that. And double check the way StatKey has the data. I think we want mu n minus mu e. So they have the no's minus the yeses. Yep, that looks right. And so we're looking at the mean difference of those. Let's call that mu d, which is the mean of the no's minus the mean of the yeses. Yes, I think exercise matters. And then we have this sample. And sample size total was 75, 34 plus 41. 75 hotel workers. Pretty sure they were all female, which is interesting. Some gender bias going on there. And they had an X bar for the nose that was, I think, negative 0.2-ish. Yep. And then negative 175 was the other one. And then X bar for the exercise people, negative 782, was it? 75. And we took those two together to get this new one, X bar D, which is our estimate of what's going on in like a general population, which is just the difference of these. So X bar don't know minus X bar I know exercise matters, or I was told it, And if we take a negative minus a bigger negative, we end up with a positive value, and that was that 1 point, was that 5, they rounded it to 1.59, I think. Okay, so the difference I don't know versus I do know, which shows that there was more of a weight loss from the people who thought exercise mattered to the people who didn't know exercise matters. So now we have to decide what's the alternative hypothesis, because this study, I don't know if they really came out and stated it, did they? Let's look back at the study. So they're just kind of doing an abstract stating what they think their conclusion was. So as a result, compared to the control group, they showed a decrease in blah, blah, blah. These results support the hypothesis that exercise affects. Okay. So they're not saying, so here's the question. What are they saying? Are they saying that we expect people who think their job is exercise to lose more weight? Or are they saying we expect that there will be a difference? So we have to decide on that. So what's the difference between those two statements? So we have two options for an alternative I get from reading that. Our alternative could either be that the mu here, that the difference should be greater than 0, or that the difference is just not 0. It just doesn't matter. Could be more, could be less, I don't know. So for sure, we have a null hypothesis that says the people who exercise is going to be the same on average as the people who have no idea that their job is exercise. Sometimes we write that by subtracting one to the other side. So mu n minus mu e, put those in the right order this time, yep, is 0, which says that the difference is 0. And so the alternative hypothesis could be a greater than, or it could be a not equal to, and we have to make that decision. So I'm thinking that they were expecting, you know, we think mindset matters, placebo or not. So they were thinking that it was greater than versus a not. So if it's greater than, then we have to run a right tail test. That's why this is important to decide. Or if it's not equal to, then it's a two-tail test. So since nobody's chimed in, I'm going to go with the conservative idea that it's a two-tail test. So I'm going to say the alternative is that we don't know. We don't think it's going to be 0, which means it could be more, it could be less. So that would be saying, let's see, that mu e is not equal to mu n. Alternative version of that would be mu e minus mu n is not 0. Or we could say, hey, the difference isn't 0. So this says there's no difference. This one says there's a difference. Remember, no difference means the difference is 0. All right, so that one always I have to think quite a bit about. So we're going to run a two-tail test on this, and it's important because we haven't done that yet. So I had already the data here. They already picked the hypothesis for me, and so then I generate. I have 6,000. I'm going to go one more for 7,000. I'm going to run a two-tail test. Okay, on a two-tail test, we still have to plug in our data value. Our data value is 1.59. Now, I can't just plug it in on the left because negative numbers live on the left. You got to plug it in on the right side of the null. That makes it, a two-tail is more complicated for several reasons. So I come down here, I plug in 1.59. And then StatKey then recalculates a similar number for the other side based on this data. And the p-value are both of these numbers right here. So that into my picture, which I have yet to draw. Typically with a two-tail, we use both of the numbers. Theoretically, they should be the same number. So here we have our mu difference of 0. And then where did our data land? We want to put it in the right spot. Did the data land near the middle or away from the middle? So it's a little bit away. So over here is my x bar d, which is the 1.59. And because this is a two-tail, I have to also plot the number on the other side. And in this case, that would be negative 1.59. And I need both of these tail probabilities in this case. So the p-value is the combination of this one with a two-tail test and this one. So the p-value in this case is the sum of those two numbers. And again, ideally they should be the same in an ideal world, but this is a simulation. All kinds of random stuff happens in reality. So sometimes they won't be exactly the same. So p-value is going to be the sum of those two, so that would be 0.0, that would be a 108. And sometimes we round that to a certain place. I'm just going to go with it right there. As a percentage, oh, that's not p, it's the p-value. Oops. P-value, usually p means proportion. We could also state that as a percentage, so moving the decimal twice, that would be 1.08%. Typical significance level is 5%. So that would be the idea of alpha. So unless it said, hey, use a 1% level or a 2% level or a 0.5% level, we go for a 5% level. And my p-value, 0.0108, is definitely smaller than 5%, 0.05. So then my decision should be reject the null hypothesis. Reject null. And then we have to come up with our conclusion. What does that mean? Okay, so in this case, since we were in a two-tail test, what it means is we have evidence in favor of the alternative that there is a difference in the average weight gain of people, or weight loss of people who believe exercise matters and people who don't know exercise matters, I think is the way I would state that. Could I have made a mistake? There's a 5% chance I made a mistake in this. So, conclusion. We'll talk about making a mistake. There is strong evidence that knowing exercise makes you healthier. Let's see, there is strong evidence that knowing exercise makes you healthier leads to more of a weight change, leads to, it's always the hard part. How do we word this? Than not knowing exercise matters. Now, I'm pretty vague about the weight change here, although my data showed more of a weight loss. Notice I didn't use the word loss here. I didn't use the word loss specifically because my alternative hypothesis was the not equal. Like I'm saying, hey, I really don't know what's going to happen here. Let's see. Somebody else might say, oh, I think it's going to matter, so I'm going to go for an alternative where it's greater, in which case their conclusion would just be written different. they would say, instead of change, they would say more of a weight loss. And again, I'm using the word change here, so I'm going to emphasize that, because my alternative hypothesis, so I'm being a little more vague, because my alternative hypothesis was that there was going to be a difference. The difference is not going to be 0. I don't know if it's higher or lower. Had I instead chosen that greater than hypothesis, then I would, instead of the word change, I would have used the word loss there if my alternative hypothesis had been the mean difference is going to be greater than 0. All right, I could have made a mistake. So let's talk about the mistakes here that we can make.